Right. Thank you for the introduction, and I also want to thank you for the invitation to Korea. This is my first time. I'm already enjoying it a lot. It's a very nice country. Today, I'm very happy to be the first speaker. I'm going to tell you something about a Hele-Shaw problem. In particular, it's a homogenization. So I hope it's going to be interesting for you. What I'm going to tell you is about some new results on the homogenization of the Hele-Shaw-type problem. But what is important, it's in a time-dependent periodic media. The time dependence here is important because the media depends also on space, but in time-independent media, this problem has been completely solved already. But it turns out the time-dependent case is qualitatively completely different, so it's interesting to consider this generalization. So first, let me... This was working. I'm sorry. It was working just a moment ago.
Was it working?
Yeah, I was trying to. That's okay. I can maybe just use this space.
Okay. So,
I don't know. Alright, so let me introduce the Hele-Shaw problem. This was introduced in 1898 by Hele-Shaw to model flow of incompressible fluid in something that is now called a Hele-Shaw cell. Hele-Shaw cell is a very simple thing. You have two parallel plates very close to each other, and in one of those cells you have a hole, and you are pumping a liquid into the space between these two cells. So it's working. Okay, thank you. So you are pumping the liquid in between these two cells. So initially you have some wet region filled with liquid, and then when you are pumping the liquid in, this region is going to expand. It turns out that when the velocity of this flow is small, the flow of the fluid is completely pressure driven. That means that the velocity of the flow is given as the gradient of the pressure U. And since we are assuming incompressible liquid, we have the divergence of the velocity is equal to 0. When you put these two equations together, you get that the pressure must be a harmonic function inside the wet region, right here. The pressure outside, this is the air or vacuum, is 0, so the pressure on the boundary is 0 as well. And from that we can get the velocity of which this interface between wet region and dry region is going to move. And it's going to move exactly with the velocity that is given as the norm of the gradient. So this is a problem in 2 dimensions, but it turns out that this problem naturally generalizes to higher dimension, n greater or equal than 3. In 3 dimensions, this is a natural model for a flow of incompressible fluid in porous medium. So the situation is following. You have some kind of sand, porous medium, and you are pumping liquid, let's say water, inside this medium that fills some space. There's a free boundary between the wet and dry regions. And it turns out that, again, this is the same velocity law that you will get for these kind of problems. So let me be precise in what kind of problem we are studying. So we take the dimension, space dimension greater or equal than 2, and we take a domain in Rn, which is simply a domain can be unbounded, but the boundary must be a compact Lipschitz boundary to have some kind of nice closeness of the problem. And we are solving the problem on some parabolic cylinder, omega times the time interval, time is a positive constant. And the problem that we are gonna look at is this following Hele-Shaw-type problem. We are looking for a pressure, U, defined on the domain Q, that is non-negative, and it formally satisfies the following 2 equations. The first one is, as I said, the pressure must be harmonic inside the wet region. The wet region is characterized by this pressure being positive. So this is where we have water or liquid. And harmonic in space only. So for each time we have a harmonic function. The second condition is the motion of the free boundary, the interface between the wet region and the dry region. This is defined as the normal velocity of the free boundary. This free boundary is the boundary of the positive set, the wet region, moves with a law that is given as the gradient, the space gradient of U. So this is the space gradient. And we take the modulus. And now what we could do, or we can do, and it makes sense actually, to consider a medium that is not homogeneous, that depends on space and time. So this is this constant that determines how fast the boundary moves. So this is the standard Hele-Shaw problem. Of course, we want to consider some kind of initial and boundary conditions. So let me show you how you should think about this problem. So this is the boundary of this domain omega. The domain omega is outside everywhere, where we are looking for the solution. And you should think about this, complement of omega as the source. So through this place, we are pumping in the liquid inside, let's say, the Hele-Shaw cell, in such a way that we are keeping a constant pressure on the boundary of the domain. And this pressure is some prescribed function psi that can depend on space and time. The second, this is the boundary condition. The initial condition is simply the region that is initially filled with the liquid, this domain omega 0. So its boundary is this gamma 0 at time t0. So we simply say that the positive set of u is equal to omega 0 at time equals 0. Then as the solution evolves with this free boundary velocity given as the gradient times this constant g, it's going to move to some new boundary gamma t with this normal direction nu. And again, the wet region and the dry region are characterized by the fact that u is positive in the wet region and 0 outside. So now since the problem depends on space and time, what we want to look at is that does the inhomogeneity of this x influence the flow when we look at the problem from far away, so we don't really see the inhomogeneity anymore. And this is the question of homogenization. So to make it formal, what we are doing, we are solving the same problem, the Hele-Shaw problem, but for function u epsilon depending on some new parameter epsilon, positive. And in such a way that everything is the same, all the equations. The only difference here is that we rescale this inhomogeneity g using this parameter epsilon. So g depends on epsilon, x over epsilon, and t over epsilon. What this means is simply that the size of the inhomogeneities has some kind of size epsilon, and when we set epsilon to 0, this oscillation grows, and essentially it represents the fact that we are looking at the problem from far away. And we consider the same initial and boundary data for the problem. And now we want to ask two questions. First question is, does u epsilon have a limit as epsilon goes to 0? Right? So this means that it converges to some unique function, right? The homogenized solution. And what is this homogenized solution u? This is the second question. And I'm going to try to answer both of these in this talk today. So let me continue. For this problem to have some kind of reasonable behavior, for example, so we can expect actually homogenization, we need to impose two sets of assumptions. First is just to get a well-posedness of the problem. This is actually not completely trivial. The reason for that is that the boundary of the wet region can collide when the problem evolves. So you can have topological changes of this positive set, the wet region. So you cannot have classical solutions for all times. So you need some kind of weak solutions. In this case, it turns out that the good notions are the viscosity solutions defined using a comparison principle. This problem satisfies a comparison principle. So that is a reasonable notion of solutions. So let me make two assumptions. First, the regularity of g. Simply g is a Lipschitz function, and non-degeneracy. What I mean is simply that function g is bounded from below and above by some constants for all x and t, and the constants are positive. So in particular, what this means is that the boundary cannot stop, right? Because the boundary is given as this g times the gradient, as long as the gradient is non-zero, and this is always non-zero because it's a harmonic function, the pressure is a harmonic function, the boundary is not going to stop. If it stops, this is a very bad for uniqueness of the solutions. And this second set of assumptions that we need is to get some kind of averaging if an epsilon goes to 0, right? And for this, I'm going to use some periodicity of this function g. So we will assume that this g is a zn plus 1 periodic. What that means is that we take any shift, kl, from the integer lattice, and we shift the medium by this shift, we see exactly the same medium. So it's a periodic function, right? So with these assumptions, we should have some kind of averaging behavior. So now I'm going to postulate this. So if the problem homogenizes, U epsilon, the solutions of this epsilon problem, should converge to some kind of solution of a problem that should be similar to the Hele-Shaw problem. So first of all, we realize that U epsilon are harmonic for all epsilon. So the limit should be a harmonic function as well. The second thing is that the free boundary velocity we knew should not depend on space and time anymore, but it depends on the gradient again. But we don't know what the dependence is, and actually this turns out to be the question. What is this dependence on R? Right? And of course, when you have problems like this, you have to ask the question, are these problems well posed? So this is the first thing that we have to answer. So I'm really quickly going to answer the well posedness of this problem. So for this, we need two assumptions, again, for this R. This is the non-degeneracy that you saw before. Again, that the boundary cannot stop. This RQ, the Q is the gradient, is bounded from below by some positive number times the gradient, and from above as well. But now, it turns out that the homogenized velocity is more complicated. So we have to allow for much more general functions R. So what I'm going to do, I'm not even going to require that R is a continuous function. The only thing that I'm going to require is that R is some kind of monotone on the rays, on the lines from the origin, in the sense that if we take the upper semi-continuous envelope of R at some point Q, this must be always less or equal than the lower semi-continuous envelope at a point at a vector farther away from the origin. So this is, I call this ellipticity, and this is essentially guarantees that the problem has a comparison principle. And we can define a reasonable theory of viscosity solutions. So this is the result. For both problems, for the epsilon problem with the G, the velocity is this F, the free boundary velocity. And if F is this function R, that satisfies the assumptions on the previous slides, then the problem, this kind of Hele-Shaw-type problem is well posed. It has a unique viscosity solutions for sufficiently regular initial and boundary data. I'm not going to specify what this is, but in simple terms, the comparison principle that we can get for these viscosity solutions requires strictly separated initial and boundary data. And so to get a uniqueness from comparison principle, we need to perturb the initial data. And to be able to perturb, we need some kind of regularity, but it's a very weak regularity. For example, the initial boundary omega 0 is only C1 one function. I mean, so Lipschitz has a Lipschitz derivative. Anyway, this is not completely trivial, but this is an extension of the previous results by Inbom Kim from UCLA who studied this Hele-Shaw-type problem. And also, we have to use some new ideas from our recent work on elliptic parabolic problems to get the extension, especially for this R when it's not continuous function. Anyway, when we have the well-posedness, we can finally answer the homogenization question. So I'm going to state the theorem. So if we suppose that this G is the function that satisfies all these assumptions that I stated. It's a positive function, Lipschitz continuous, and periodic on the integer lattice, so Zn plus 1. And also we assume that the initial and boundary conditions are regular, so that the well-posedness theorem on the previous slide holds. Okay? So when we assume this, we have the following result. There exists a function R from vectors to some non-negative numbers that is non-degenerate and elliptic. What that means essentially that it satisfies the assumptions that I had on the two slides before. So the guarantees that the homogenized problem actually is well posed. And the conclusion is that the solution U epsilon of the inhomogeneous epsilon problem, with the G depending on X and T, with the given initial boundary data, converge as epsilon goes to 0 to the solution, the unique solution of this homogenized Hele-Shaw-type problem. Right? Now the convergence is in the sense of how relaxed limits. This is a notion of limits in the theory of viscosity solutions. It's not very important. The important thing to notice is that U doesn't have to be a continuous function, so we cannot expect uniform convergence, but this is the next best thing that we can get. In particular, if this function U is a continuous function on some compact subset, then the convergence is uniform. The other thing in this theorem is actually that the free boundaries, the set partial, the boundary of that region, converge locally uniformly in the sense of a Hausdorff distance to the boundary of the limit problem. And this is very important because, of course, we care about the boundary of the wet region. This is the important thing that we are looking at. Okay, so this is the final theorem, and in the rest of the talk, I'm going to try to explain how to obtain this velocity r, and why this problem is very different from the time-independent case, and why it's actually worth to look at this. So the question is, we have to ask, what is the form of this velocity rq? Right? This is not completely clear. Let me give you two examples. First one is when g is independent of time. So gxt is equal to gx, right? So this problem is actually completely solved. This was solved for the Hele-Shaw problem by Invon Kim from UCLA again. For periodic g, using completely just viscosity methods. And then it was extended by Kim and Melle in 2009 to random case. So then the g can be random, stationary, ergodic function. Also, I did some asymptotic behavior, but it's not so important. The function r in this case is very simple. It turns out to be just a constant times the norm of the gradient, right? And this constant is actually given explicitly as 1 over the average of 1 over g. Now, this might seem a little bit surprising, but it's actually not very surprising, because what we are doing, we are averaging velocities over a distance. So we are taking the average velocity over some distance, and when you do this computation, you get exactly this kind of value. But the important thing here is that this is a simple relation. So what I proved is essentially that the solutions of this problem, with g depending only on x, converge, epsilon goes to 0, to this simple Hele-Shaw problem. This is just a rescaling of the standard Hele-Shaw problem with constant data, right? So what is the behavior like when the g depends on t? Well, let's have a look at the one-dimensional problem, because here the situation is very, very simple. So what I'm going to do, I'm going to solve this Hele-Shaw problem on a domain 0 to infinity, just the right half of the real line. And I'm going to assume that initially the region filled with water is from minus infinity to x0. x0 is the initial point of the free boundary. Free boundary is just a point at this one-dimensional setting. So what I have is actually that the free boundary will have a location at point x of t. It is going to move in the direction of the normal vector, which is simply this direction to the right, right? And I'm going to have some kind of boundary data at 0. So u is equal to psi is the given function at 0. So the first thing that we can see here is that actually when you have a harmonic function u, the harmonic functions in 1D are just linear functions, right? So that means that this gradient of u at this point is given actually by just the slope of the linear function, right? This is just the ratio between psi and x. So this is very simple. So the only thing that is left is the equation for the normal velocity. And the normal velocity in this case is just the time derivative of x, right? So the time derivative of x satisfies now just an ODE. So the whole Hele-Shaw problem reduces to an ODE equation for this x epsilon, for each epsilon. And this is how the ODE looks like. So you have the function g and the x dependence, t dependence, and then the gradient here. Initial condition is x of 0 is equal to x0, right? Very, very simple equation, it looks like. So what we want to do to homogenize the Hele-Shaw problem, we want to homogenize this ODE, right? So you can say this is simple enough, but it turns out that actually the results are pretty recent for the homogenization of ODEs like this. So the first result is for Piccinini from the 77, but he assumes that this is a constant, so this is not there at all. Much more recent result, Ibrahim Mono from 2008 actually answers the question of homogenization of this kind of equations. So the result is that x epsilon, the solution of this equation, converges to function x locally uniformly as epsilon goes to 0. And now the function x satisfies the Hele-Shaw velocity law for the homogenized problem. So the velocity, normal velocity is equal to r times of the gradient. The same boundary initial data. And they actually have some rate of convergence, but it's not very important for us. But the funny thing about this, a very interesting thing about this, is that the r doesn't have an explicit form. I mean, it really depends on the function g. And the only thing is that we have this estimate that rq is between the minimum of g and maximum of g and times the absolute value of the gradient, right? This is the only thing that we have. And actually both of these values can be attained, even in one problem. So let me give you an explicit example to see how different this is. So this is a very simple medium. Gx of x of t is sine squared pi x minus t. Plus 1 to make it positive, to satisfy this degeneracy. We can solve this explicitly as an ODE, and then we can plot the velocity of the free boundary over the gradient q. And what we see here is this interesting effect that the velocity rq is actually increasing in the gradient, but at some point it becomes a constant. So this is a constant. And I call this here velocity pinning effect. So it means the velocity is pinned to one fixed number for some time, and then it starts increasing again. And it looks like that the function is actually Helder or something, but it's not differentiable at this point. So this is an interesting behavior. The left part of the picture is when the boundary is moving in the opposite direction, to the left on the on the real plane. And you can see that the relationship is very simple. It's just a line. It's almost the same as for the time-independent case. So you can see that you have a directional dependence, and you have this strange behavior for the function for the function r. So this is the thing that makes this qualitatively completely different from the time-independent case. You have this velocity pinning. You don't, in the time-independent case, you have just a line here. So we have to account for this when we are doing homogenization. We have to develop something that allows for these kind of things. Fortunately, the spinning effect doesn't happen at the origin. So in the origin, we always have this kind of corner. This is important for uniqueness of the problem. Of course, one can cook up even more interesting examples where this is more complicated, but you have a couple of these pinning regions, and it's different values if you go to the right or you go to the left. It somehow coincides when you look at the function. Let's go back. What is the cause of this? The cause is when you look at the maxima and minima of this function. This is somehow something going, the maxima and minima are on lines that go like this in the x and t plane, right? So the medium is not symmetric when you go to the right and when you go to the left. So this is the cause of the spinning effect. All right, so this is the reason why this is a qualitatively much more complicated problem than the time-independent homogenization. So let me tell you how to identify this RQ in the homogenization theory. I still have 20 minutes or 15 minutes, right? So the standard arguments in the homogenization for viscosity solutions, the first actually paper comes from the homogenization of Hamilton-Jacobi equations, I think, by Leons, Papanikolaou, Radhan from '87. But this is a very famous unpublished paper. I think one of the most cited unpublished papers. And then by Evans in '91. And for elliptic equations by Evans in '92. But let me tell you what the two-step process is. First, we want to identify the candidate for the homogenized problem. And the way to do it in this setting, the periodic setting for viscosity solutions, is to find something called a corrector. And this is a fancy name for just a global periodic solution. So we find a global periodic solution, and it turns out that the solution exists only for a very specific value of some constant. So when we are homogenizing Hamilton-Jacobi equations, I don't know if you've seen it before, but you want to homogenize equation h dv of x is equal to 0. So what do? You want to, for every p, find this number that is unique actually. This is the candidate for the homogenized operator that doesn't depend on x, such that this equation has a global periodic solution. So, and this value is actually unique. This is provided by the theory of viscosity solutions, right? And the second step is we have this corrector, global periodic solution. So what we can do, we can prove that the limit of this epsilon solutions of the inhomogeneous problem is actually the solution of the limit equation, which is just the h of dv is equal to 0. Using this Evans's pair-trip test function method. So it was introduced, I think, in his paper '91. And essentially, viscosity solutions test solutions using a local condition. But when you're doing homogenization, you in some sense have to transfer some kind of non-local information about the operator, how it behaves over a period. And it turns out a convenient way how to do it is actually to just solve the equation and get a global periodic solution. This gives you information about how the operator behaves on long scales. And then you can use this information perturbing the test function and getting this non-local information into the local condition for viscosity solutions and getting the limit. Unfortunately, this doesn't apply to free boundary problems like a Hele-Shaw problem. The reason for this is because it fails at both steps, actually. The corrector, we cannot expect to have a periodic solution that is globally defined. There will be just a constant function, right? And the perturb test function method doesn't work because the level set 0 is somehow special for this problem. This is how we can tell the difference between wet and dry regions. So we have to devise a different approach, and the approach is use an obstacle problem, some kind of obstacle problem. Again, this is a little bit was applied to a different set of equations. First, by homogenization of elliptic equations in the random case by Caffarelli-Souganis 1 in 2005. This is a pretty famous paper, and then successfully applied by Inmon Kim to Hele-Shaw problem homogenization in time-independent case and other equations like contact angle dynamics. And let me explain what this says. So suppose again, I'm coming back. We want to identify this function RQ. We guess that the problem homogenizes, that U epsilon converges uniformly to U, right? Now U, we say, satisfies this kind of homogenized problem. So it's harmonic function velocity is equal to R du. Well, this is a very simple problem. So it turns out this problem has traveling wave solutions. Let's say traveling wave. These are just these plane solutions, right? So we have a plane. This is an explicit form for that, but this is a plane with the gradient Q. This is the slope. And moving the boundary, which is just the 0 level set, is moving in the direction of the normal vector with velocity R, right? So we have this parameter Q and R. This is why we define PQR. So we have a whole class of these kind of traveling wave solutions, right? And a quick observation is that this PQR is a solution of this problem if and only if the R is the correct RQ, right? So this is the correct velocity. So the question is how do we use this to find the homogenized velocity RQ? And the idea is pretty simple. I mean, what we can do is that we take Q, this is the gradient, non-zero, and we can solve this Hele-Shaw problem, the epsilon problem, with the initial data that coincides with this moving traveling wave solution, PQR. So we take the boundary data, which is exactly equal to the solution PQR at time equals 0. So this is just the form of this at time is equal to 0. Right? This cancels out. And we can do this for every epsilon because we have these epsilon problems, and for every Q. But the Q is fixed, let's say. That's a fixed function. And now we look at the evolution of this solution. So it turns out that if we take the R to less than the actual velocity, homogenized velocity, then in some sense, when we set epsilon 0, the traveling wave solution PQR should evolve slower, right, than the actual solution, because the actual solution converges to the real solution, which is faster, right? So this gives you that information that we have too little R. On the other hand, if R is too big, then this PQR should evolve faster than this U epsilon Q, which should be this PQRQ. This RQ is now less than R, right? So I hope this kind of makes sense, because this is the way how we can test. But the difficulty with this approach is that how does one solve this equation on an unbounded domain? The second thing is, what does slower and faster mean actually, right? It's difficult to somehow define. So we use this obstacle problem idea. So instead of solving the problem on the whole domain, we solve an obstacle problem with PQR to be as the obstacle, right? So we define this kind of strange domain, which is essentially a cylinder, infinite cylinder, shifted a little bit from the origin. This is the origin right here. So that initially at time t equals 0, the PQR, the linear wave traveling solution, actually has some kind of positive set in here. So the free boundary is this one at time t equals 0. And now we solve this obstacle problem with this obstacle. What it means is essentially we just find the largest subsolution of the epsilon problem, right? But that is less or equal than the obstacle on this domain Q, this one, right? This gives us some kind of subsolution, and I'm going to denote this as U epsilon QR. This is very important. But we can do this the same thing from above. So we take the smallest subsolution of the epsilon problem when the super solution actually is greater or equal than the PQR obstacle. And this gives us we always can find these kind of solutions, and they have nice properties. For example, they are solutions at all the points where they are not touching this obstacle, and they actually coincide with the value of PQR on the boundary, and so on. And now we can use this idea to actually identify the velocity RQ. The reason for this is because this obstacle problem has a very nice natural monotonicity. I don't know if this is a very, very well-known fact. If you solve the obstacle problem on a smaller domain, then the solution is more extreme. It's definitely smaller or larger or smaller, depending on what you are taking, the largest subsolution or the smallest super solution. Anyway, let me explain the new idea in this time homogenization that is different from the previous approaches. So in the previous approaches, the way to identify this velocity was always to look at this contact set between. So this is the obstacle, this flat line, right, PQR, and when you wait until, let's say, time equals 1, the super solution is going to maybe evolve faster than the obstacle, right? So it's going to make these kind of fingers. And the previous idea was always to look at the contact set between the obstacle and the solution of the obstacle problem, and say that if there's a contact, we are moving too slow and so on, or too fast, depending on the point of view. Here, it turns out that for the free boundary problems, it's much better to look at the flatness of this problem, of the solution. And flatness, what I mean is this value, how far I move from the boundary of the obstacle, right? So I have this value phi epsilon QR for all these parameters. And it's simply the flatness of this super solution, right? And it in some sense measures how bad my guess is, my guess of R is compared to the real RQ. We can do this from below too, from the subsolution. So the subsolution, when we evolve for some time, is gonna evolve a little bit slower than the obstacle, and we measure this distance again to be the flatness of the solution. So in the last couple of minutes, let me just explain how you can actually do this in a picture, how you can identify the value, the candidate for the RQ. So we start at t equals 0, right? At the time t equals 0, the solution of the obstacle problem is equal to the traveling wave solution PQR. So we have this nice, this is the wet region with a flat boundary, the boundary of this obstacle. And we solve this problem for some time, until time t equals 1. And what we get a solution that is touching the obstacle at some points, right? And this is the largest subsolution. And if the flatness, the way how much it detaches is too small, it's not detached at all, then we know that R is too small. On the other hand, if something like this happens and there's a lot of detachment, then we know that R is too big. Right? So this flatness property tells us how bad our guess is. And we can use this in the following way. So we look at the flatness, this value, so the distance, for very small epsilon. And we look at how big the value is to compare to some kind of critical value. So when R is too small, as I said, the detachment is going to be large. But it's going to decrease, and then it's going to be very small for large R. But there's a value, some kind of critical value, and this turns out to be a very good guess for this homogenized velocity RQ. I'm writing R upper bar because this is one candidate. We can do the same thing for the super solutions. And again, we start from the same thing. The super solution is equal to the obstacle, and we solve the problem for some time until time equals 1. Again, depending on what the flatness of the solution is. If it's too big, then we know that R is too small. If it's too small, then we know R is too big. So the same idea but reversed. So we have this flatness of the solution. For big R it's too big, for small r it's too small. And we find this critical value RQ. So we have two candidates, right, for the RQ. And now we have to work quite hard to actually show that this is the same value and this is the reasonable value for the homogenized problem. And then eventually prove the convergence. So let me just explain how to take this critical value. This is a new idea in the paper, so I would like to spend a couple minutes on this. So the idea comes from this following question. Can the free boundaries of the solutions of the obstacle problem have long, thin fingers? What long, thin fingers means that if this set is somehow very long in the epsilon scale, let's say. And the answer to this question is no, and this is the following lemma. There exists a given constant that is independent of epsilon, such that for every small epsilon, we have that the free boundaries of the sub-solution and the super-solution of the obstacle problem are in between cones that are this distance apart, which is epsilon times this correction, absolute value of Ln epsilon to the power 1/2. Right? Let me explain on the picture how this works. So you solve the problem, you get some kind of crazy boundary, and whenever you take a point, you know that this boundary is squeezed between two cones, this cone and this cone. So that then in some sense mean that you cannot have like crazy long fingers of the boundary so the boundary cannot oscillate too much. This is important because if the boundary can oscillate like that, we don't expect homogenization of this problem. So this is an important property. And now to actually be able to use this kind of information, because we have this distance, this error here of epsilon Ln epsilon to 1/2, we would like to have this boundary far away from this obstacle. And how far away? Well, something much bigger than this value, right? So we can actually say something about the cone here. And it turns out that we can take some power epsilon to the beta. Whenever we take beta less than 1, this is much larger than this value. So this is a good guess for how to take the critical value of the flatness, this epsilon beta for beta less than 1. I don't know how much time do I have?
Maybe 1 or 2 minutes.
1 or 2 minutes, okay. So there's another reason why we should take some kind of beta. I'm not going to skip this. So the critical value of the flatness is this epsilon beta. So we should consider the candidates that have the flatness, this function that I defined, to be on the scale epsilon beta, when a beta is between 4/5 and 1. Right? The less than 1 is because of the cone property. And finally, we can define the two candidates of the velocity. And this is what I described in the picture, but really quick. It's just you take the supremum, the largest velocity, for which the flatness is greater or equal than epsilon to beta in the scale. Right? So this is the largest velocity like that. And then the lower velocity is the smallest velocity, for which the subsolution behaves like epsilon beta in the flatness scale. Right? So we have these two candidates, and this is the formal way how to write the pictures that I was just describing. But anyway, this is not very important right now. So now we have to work pretty hard to actually prove that we have nice properties of this candidates. So we have to use the scaling of the problem, the monotonicity, which is usually called the Birkhoff property, which is simply the consequence of the periodicity of the medium. Then the cone flatness, which is very important, turns out to be a very important property. And something called local comparison principle that I skipped. That's not important. But what we have is that actually these functions almost coincide. They are very close to each other. So one of them is just the upper semi-continuous envelope of the other, or lower semi-continuous envelope of the other. So they cannot have some crazy behavior. And it turns out that actually monotone in this particular sense, that if we look at the lower velocity at some point q, it's always less or equal than the upper velocity a little bit farther from the origin, AQ. So this gives us the two conditions that we need for the well-posedness of the Hele-Shaw problem. So what we do, we set RQ to be, for example, the lower velocity. It doesn't really matter. And then we can prove that actually the limit u of the u epsilon solves this homogenized problem. this is what I wrote a couple of times before, but with this particular choice R, which is this is the candidate. And this finishes the proof of the theorem. So let me just give you what are the open problems. So first of all is the continuity of RQ. So I expect that it's going to be continuous, but I just don't know how to prove it right now. Also, Hölder continuity is probably the function should be Hölder continuous even. This should be important for the study of rate of convergence of this problem. So if we want to study how fast the U epsilon converges to U. And now, why this new approach I think is very important is that it might allow for the study of random environments for free boundary problems. And this is a difficult open problem for more general free boundary problems. And also, I would like to know if we can extend this idea of flatness to epsilon beta scale to some other problems that are non-monotone in this weak sense that, for example, Hele-Shaw with mean curvature term, or problems coming from contact angle dynamics, and so on. All right, so thank you very much for your attention, and I'm happy to answer any questions.